So I hope I am audible. Could you please confirm, am I audible?
Yes, audible.
Thank you. All right. So welcome to the week 7 problem solving sessions of the course Strategy and Introduction to Game Theory. I am Shubham Keshri and I am a PhD student at the Department of Management Sciences, IIT Kanpur. I am one of the TA for this course, and this will be the second last session. So in this session, so the format of this session is as follows. We will discuss problems, and through this discussion of problems, we'll go through the concepts that was discussed in the lectures. At your end, you will not be able to see the option of chat. So if you want to communicate, please unmute yourself and speak. All right? Yeah. So we will proceed. Okay. So in this week's lecture, we talked about evolutionary stable strategies. So this kind of consideration of game theory is different from what we have seen so far. And we'll see how it is different. First, let us see what the question says. It says that which of the following statements are correct. If SS is strict NE, so this strict means strictly dominant Nash equilibrium, all right? If SS, so suppose S comma S, so S is the strategy of the first player and the second S is the strategy of the second player. So if S comma S is a strict NE, then it is a ESS. So ESS is evolutionary stable strategy. So this is the first statement. The second statement is strict NE is sufficient but not necessary for evolutionary stable strategy. And the third statement is a weak NE is always a evolutionary stable strategy. So over here weak means weakly dominant Nash equilibrium or weak dominant Nash equilibrium, whatever you say. Alright. So these are the three statements. Have a read. If you don't understand, we'll discuss and then we can proceed. So have a read, and if you know the answer, you can, or you want to discuss, we can communicate. Alright.
I would say it is either B or D because 3 is out of option, that I am very sure about it. But
okay.
I mean, the lectures that I have attended till now. So on the basis of that, I can say if it is Nash equilibrium, it is not for sure that it is also an ESS. But if it is an ESS, yes, then it is a Nash equilibrium. So this is what I know.
So you were saying that if sorry, could you repeat? If
it is an ESS,
if
evolutionary stable strategy, yeah, then it is a Nash equilibrium. But if it is a Nash equilibrium,
implies Nash equilibrium.
Nash equilibrium.
If Nash equilibrium, then ESS is not sure.
We cannot say that it is a.
All right. So here you are talking about Nash equilibrium, and mind you, in all the three statements, we are specifically talking about strictly dominated Nash equilibrium or weakly dominated Nash equilibrium, and not just Nash equilibrium.
Yeah.
So you have to be careful about that. All right. So yeah, these two things which you have said is correct, but you have to take care of these two different kinds of Nash equilibrium. The first is strictly dominated Nash equilibrium, and the second is weakly dominated Nash equilibrium. All right.
Right.
So yeah. So any idea of what this strictly dominated Nash equilibrium would do to this kind of implications? This kind of implications.
If it is strictly dominant Nash equilibrium, then a strategy of both the players will be, I mean, if they are dominant, both will play their dominant strategy. So this means that it is a strictly dominant, I mean, there is a dominant strategy. There is the same dominant strategy for both the players. Then it is a strictly dominant.
Okay, so let me give you one small example for clarity. All right. So suppose there are two players, player one and player two, and they have two different strategies, A and B. Uh, yeah, capital A and capital B. And the payoffs are, I'm writing in small letters, A comma A. So since we are talking about evolutionary stable strategies, we will always write a symmetric matrix. All right. So it is A comma A, B comma C, C comma B, and D comma D. I hope you understand why I am writing a symmetric payoff matrix. If you don't, you can ask.
Right.
All right. So you see, when I say that A strictly dominates B, then A must be greater than C and B must be greater than D. So this is the condition for strict domination of A over B. All right. Is it
Okay.
all right?
Yeah.
So when I say A strictly dominates B, then the payoff which I get for the fixing a strategy for the other player, the payoff which I get when playing A is strictly greater than the payoff which I get when playing B. And we should also consider the other strategy for the second player as well. So this gives from the first strategy of player 2 and this gets from the second strategy of player 2. Now you see, if I write, so suppose A is over here S because we are talking about S comma S. So if I say SS, SS, and S is strictly dominant strategy.
Excuse me. Can't we say A is also greater than B and C should also be greater than D from the perspective of player two?
So from the perspective of player 2, when I say A strictly dominates B for player 2, so I'm talking about the strategies of player 2, A for player 2 and B for player 2. In such case, you have to say then player 1, we are fixing the strategy of player 1 over here, then it will be, this is the payoff of player 2
Player two.
when
Right. In that
he plays
also
A,
is
and this is the payoff of player 2 when he plays
right.
uh,
Okay.
B. So it is always A greater than C and B greater than C, both cases. All right.
Yeah.
Okay, so when I say S is strictly dominant strategy, then you see when S is strictly dominant over all the other strategies, there might be many other strategies, not just two. There can be many other strategies. But if I say S is strictly dominating those strategies, then this condition A is greater than C and B is greater than C is met. All right. Now, if you go back to the lectures and see the conditions for evolutionary stable strategies, or uh, so these two conditions you're talking about, in those conditions, professor has stated that if S comma S is evolutionary stable strategy, sorry, ESS. Not able to use. Just a minute, right? Not able to use. Not able to use erasers. All right. So when I say when S comma S is a evolutionary stable strategy, and we have the payoff matrix as A comma A, B comma C, and C comma B, and D comma D. Then in the lectures, professor has strictly said that A should be greater than C, or if A is equals to C, then B is greater than D. So when these or this, either of the condition holds, then S will be, so if this is S and this is suppose S bar, S star, S dashed, then S comma S will be evolutionary stable. All right.
Right.
So if you don't understand what this means, I can go over and explain why this, when these two conditions hold, then S comma S is evolutionary stable. Do I need to do that?
No, this was clear.
Okay. So you see, in our case, if S is strictly dominant, this condition will always hold. So we don't need to bother about this condition. Therefore, if S comma S is a strictly dominated Nash equilibrium, then it will always be evolutionary
Yes.
stable strategy. So this is true. All right.
Right.
Now there is something necessary and sufficient condition. You have to understand the difference between a necessary condition and a sufficient condition. So could you tell me what is the difference between the two kinds of conditions, a necessary condition or and a sufficient condition? You could try, it may be correct, it may not be correct, it doesn't matter. If you're speaking, I'm not able to hear you. Right? Okay, so I'll help you. You see, when I say a necessary condition, it means that suppose you see that B is true when A is true. So when I say statement B is true only when A is true, it means that A is necessary for B to be true. All right, so A must occur such that B is true. This is necessary condition. So if A is not true, then we can surely say that B is not true. But sufficient condition is that, so when B is true, it is seen. I don't have it, sir. Okay, so what I'm saying is sufficient condition. It says that when B is true, then C is always true. So when I say when B is true, C is always true, it means that whenever B becomes true, C is always true. Therefore, if you see that the statement C is true, you may not be able to say that B is true. You see, when B is true, you are sure that C is true. The statement says that when B is true, then C is always true. But the other way you cannot say. When C is true, you don't know B is true or not. Therefore, this is a sufficient condition. So C is sufficient condition for B to be true. If you prove that C is if you prove that B is true, then you are surely sure that C is true. If you prove that B is true, then you know for sure that C is true.
So
this
B
is
is
the difference.
sufficient condition or C is sufficient condition for
So
B to be true?
over here, B is sufficient condition for C to be true.
Okay.
Sufficient condition means कि ये हो गया तो पक्का हो गया है. All right. So it means that this is sufficient. इससे ज़्यादा और कुछ आपको नहीं show करना है. And necessary means that if this is not true, you are sure that the other thing is not true.
Okay.
Okay. So you see over this says that strict NE is a sufficient condition but not necessary for NESS. You see, condition 1. This is strict NE. What is this? This is strict Nash equilibrium. So when this is strict Nash equilibrium, you see this implies evolutionary stable strategy. So when A is greater than C, that it is surely a evolutionary stable strategy. But the other way is not true, because this can also be a evolutionary stable strategy. And when this is a evolutionary stable strategy, you are not sure, not strictly, sorry, it is strictly, not strict any. All right. So this is a sufficient condition, but not necessary condition. So this is also a true statement. Is this all right?
Okay.
So, and this is not true. You can just show, because you see, when A is a weakly dominated Nash equilibrium, so what does it mean to be a weakly dominated Nash equilibrium? So I will just write it. Suppose S comma S is a weakly dominated Nash equilibrium. This is the shorthand of writing the same thing. Then a strategy or the action, you can write. Then the action or strategy maybe. Strategy A is greater than equals to the other strategy. Suppose C is the other strategy. So this is greater than equal to. All right. So it is not strictly greater than C. Therefore, this may hold, but you are not sure if this will hold or not. And therefore, this is a false statement. All right. This is a false statement. Therefore, B is the correct answer. Is this okay?
Okay.
Any doubt?
No.
Others? Okay, so I'll move forward. Okay, so this is a game. This is the Beetle game which was shown in the lectures. Same similar kind of game. So you can just take a minute and read the game, and you would have to say what is the evolutionary stable strategy. I have taken this example because I wanted to go through the steps of showing a strategy to be evolutionary stable. So just go through it. You may know the answer already, but or may not be because the payoffs are changed. But yeah, go through. So can you right away tell me what is the correct answer for this problem without solving? Is there a way to do that?
Small beetle is evolutionary stable.
So you are suggesting small beetle is evolutionary stable. Why is it so? Why are you picking up small beetle?
I remember the lecture. So in that the graph was drawn, and small beetles are evolutionary stable because if a large beetle was population, a small population of large beetle is introduced into small beetles, and then I mean, perhaps I'm wrong. If large
Okay,
beetles are introduced into small beetles, they eat away their resources and they just push these small beetles away out of the fence. And so large beetles dominates small beetles. But when small
okay.
beetles are introduced into large beetles, they don't wash out large beetles. So large beetles are
So
evolutionary.
whatever statement you are saying is based on the payoff matrix given in the lectures. This is a different payoff matrix as that given in the lectures. So that statement might be true, might not be true. So basing your assumption that that statement will hold true over here is not correct. All right. So what I'm trying to say is whatever conclusion you have drawn is from the payoff matrix which was given in the lecture. This is
Right.
not the same payoff matrix.
Okay.
Okay, so that logic might not hold here. It might happen that the answer you are saying is correct, but that logic might not hold.
Okay.
Okay, and before proceeding on the solution method, which was shown in the lectures, we can solve this problem before going into any of that. You see, find the Nash equilibrium. You see, I cannot use any other color. I don't know why. Okay, so you see, when uh, SB of the, so I'll name player 1 and player 2 for my convenience. This is not the case in evolutionary strategies, but nevertheless I'm using it. So when player 2 is playing SB, LB, when player 1 plays LB, he is better off. Similarly, when player 2 is playing LB, player 1 playing LB is better for him. On the other hand, if player 1 plays SB, player 2 is better off playing LB, and when player 1 plays LB, player 2 is also better off playing LB. Therefore, this is a Nash equilibrium. Alright? Is this alright?
Yes.
Now, you see, this is not just a Nash equilibrium, this is a strictly dominant Nash equilibrium. You see, this payoff is strictly greater than this payoff is strictly greater than this payoff is strictly greater than this, and this payoff is strictly greater than this. So this is not just a Nash equilibrium, this is a strictly dominated Nash equilibrium.
Okay.
Now, in the previous problem, when we had seen that if you have shown that it is a strictly dominated Nash equilibrium, then it will always be an evolutionary stable strategy. Therefore, strict Nash equilibrium is sufficient to show that it is a evolutionary stable strategy. So for this example, you can be sure that large beetle is a evolutionary stable strategy without even going into the solution of this problem.
Okay.
Okay. Now, with this idea, we'll just move on to solve this problem and see how this idea of game theory applies to evolutionary game theory. Right? So I'll just write the payoff table SB, LB, and the payoffs are 5, 5, 11, 1, 1, 11, and 2, 2. Just a minute, I'm not able to use this thing. Okay, just give me a minute. Just log in maybe. Because the nothing will be saved if I don't sign in. Alright, now maybe it will work. Yeah, so I'm sorry about that. All the annotations has been deleted. So I would try to take a picture and then post it in the, save it in the. Okay. So now we will work. So what are we talking about? We'll just draw the payoff table. It is 5, 5, 11, 1, 1, 11, and 2, 2. So this is the payoff matrix. Now you see what happened actually is researchers were studying about this evolutionary phenomena which occurred in living organisms. So there were some population of small beetles, and some mutations were introduced in some other form, and some of these mutations were introduced in this new population, and they were trying to understand which population will thrive. Will this old population will thrive, or will the new population thrives? And what eventually happens, what constitute the new population? So this was the question researchers were trying to understand. So while they were modeling this problem, they saw that this problem became similar to the problem of game theoretical approach. So they can be solved using game theoretical approach, and therefore this evolutionary game theory came into picture. Okay? So this is how it was conceptualized. First, they were studying a different problem, but when they modeled it and in the solution technique, they saw that they can use game theory to solve this problem, and therefore this branch evolutionary game theory. All right. And this is the context we are going to study these games in. So suppose the entire population was of small beetles, and a very small number of large beetles were introduced in this population. So this quantity of large beetles which were introduced, we will say it is X. So X is the proportion of large beetles, and 1 minus X is the proportion of small beetles. Now what they were trying to do is they were saying, if this is the mixture of population, if this is the mixture of species in the population, what is the effect of an individual which is a large beetle, and what is the effect of an individual which is a small beetle? They were trying to study that in this context. So what is the fitness a large beetle gets in this population? He gets, so this is about utility of large beetle. So he gets 11 into 1 minus X plus 2 times X. This is the utility a large beetle gets in this kind of population. Okay. Similarly, the utility a small beetle gets in this kind of population will be 5 times 1 minus X plus X. All right. So these are the two utilities. Now what they said that if one of the utility is more than the other, then eventually that species will thrive in the population and the other will be wiped out if one utility is strictly greater than the other. If that is not so, then other things can happen. All right. So we are introducing small quantities of large beetle. If the utility of large beetle is strictly more than the utility of what small beetle is getting, in that case, large beetle will thrive in the population and eventually small beetle will go extinct. So they said that let us see what is this x. So you just do 11 into 1 minus x plus 2x is strictly greater than 5 into 1 minus x plus x. If this x comes out in between 0 and 1, because x is a proportion, and we have said 1 minus x in the other case for the small beetle, if this x comes out between 0 and 1, then this will be true. All right, so we'll just solve and see if x comes out between 0 and 1. Okay. So this will be 11 minus 9x is greater than 5 minus 4x. So if you see I am making some silly errors, please stop me and correct me. All right. So it will be 6 is greater than equals to, just a minute, it will be 6 is greater than equals to, so we have 11, 9, and this is 5 and 4. 5x and x is less than 6 by 5. I have done something wrong. So what did I do wrong? I'm saying 11 into 1 minus x and 2 into x. So it will be 11 into, just a minute. Could you find the error I'm making? And this is 5 minus 4x.
Looks okay.
Seems all right, right? Okay. So it says that if x is strictly less than 6 by 5, which is always true, x is between 1 and 0. If that is the case, then large beetle will dominate in the population. And you see this holds. Or the other way, you can plot these two utilities and verify yourself. Instead of doing all of this, you can just plot the utilities. So you plot x. So this is the x-axis of x. Now you see this. This is the utility. So this evaluates to 11 minus 9x. This evaluates to um, uh, 11 minus 9x. So when x is 0, so this is 0 and this is x is 1. So when x is 0, this value is 11. And when x is 1, this value is 2. Okay. On the other hand, so this is the line for large beetle, utility of large beetle. This is utility of large beetle. I'll change the color. So this is the evaluated utility of small beetles, 5 minus 4x. So when x is 0, this is 5, and when x is 1, this is 1. So this is the utility line for small beetles. Utility line for small beetles. Now you see the utility a large beetle gets is strictly more than what small beetle gets. Therefore, large beetle will thrive. And hence large beetle is evolutionary stable strategy. Okay. This is the case when you started with a population of small beetles. You can also check the other way around. Suppose we start with a population of large beetles and then we introduce small quantities of small beetles. What happens then? In those cases also you can check and you will see in that case that large beetle is evolutionary stable and small beetle will not come over the population and capture it. Okay. So we can just go through that also to get a complete picture of what is happening over here. So I'll just take the same color, small beetle, large beetle, small beetle, large beetle, 5 comma 5. This was 1 comma 11, 11 comma 1, and 2 comma 2. Now I see the population is completely made of large beetle, and I introduce small quantities of small beetles, and this proportion is suppose x dashed because we have used x. So I will say this is x dashed and this is no, this is x dashed and this is 1 minus x dashed, the proportion of these two species in a population. Now I'll ask, what is the utility large beetle gets in this kind of population. The utility this large beetle will get is 11 times x dashed plus 2 times 1 minus x dashed. And the utility small beetle will get is 5 times x dashed plus 1 times 1 minus x dashed. If you evaluate this, this will come out to be 2 minus 10x dashed, and this will come out to be 2 plus 2 plus 10x dashed, okay, 9x dashed. 2 plus 9x dashed, and this will be 4x dashed plus 1. Okay, so these are the two utilities. You can just plot the utilities again. So this is the x-axis, x dashed axis. This is when x dashed is 0, and this is when x dashed is 1. So when x dashed is 0, the utility is 2. Utility is 2. And when x dashed is 1, the utility is, so this is not to scale, by the way, it is 11. This is the line. And for this case, when x dashed is 0, the utility is 1. And when x dashed is 1, the utility is 5. So you see, the utility this small beetle is getting is strictly less than the utility large beetle is getting. Therefore, large beetle is evolutionary stable strategy, and small beetle will not take over this population. Okay, so we have shown that this is the correct answer. In the previous also, I'll just mark this is the correct answer. Okay, so we'll move on to this next problem. In this problem, you have to find out the evolutionary stable strategy. So I am just named it as discretely A and B. Can you find out the evolutionary stable strategy? Can we use the previous logic which we used there? Let's find the Nash equilibrium first. Okay, so you see, when player 2 plays A, player 1 is better off playing B. When player 2 plays B, player 1 is better off playing A. Okay, now for player 2, when player 1 plays A, player 2 is better off playing B. When player 1 is playing B, player 2 is better off playing A. Is this all right?
Okay.
Now you see, we have Nash equilibriums. These two are Nash equilibriums. But we don't have a strictly dominant Nash equilibrium. Right? So when we don't have a strictly dominant Nash equilibrium, we cannot conclude that we have a evolutionary stable strategy. There might be an evolutionary stable strategy, but using this idea, we cannot say that there's an evolutionary stable strategy or not. Okay, so we'll have to evaluate this the way just we did in the previous question. So do you want to try on your own, or shall I proceed the way I am doing it?
Yeah, we can try this.
Okay, so I'll give you 2-3 minutes. Try. So you can just name it. This is player 1. We do not generally say player 1 in evolutionary strategy. Nevertheless, for our convenience, we are saying this is player 1 and player 2.
Okay, we do not find any evolutionary stable strategy, but we find a a point where the two lines intersect.
Right. So I will just do it again for everybody and then we'll discuss what is happening. Okay. So the utility of player one, so because I have named it player one, when he plays A, so we shouldn't say like this because this is about evolutionary stable strategy. So I am talking about when A is introduced in this mix of, suppose, so since we can take any side also. Suppose the original population was of A and we introduced small quantities of B. All right. So this is how we are proceeding. So we are saying what is the utility A is getting. Utility A is getting is minus 1 times 1 minus x plus 8 into x, and utility B is getting, sorry, utility 1 is getting when he is in B is 0 times 1 minus x plus 2x. So this will evaluate to plus x, so it will be minus 1 plus 9x, and this will evaluate to 2x. Okay. Now you can just plot to get a better idea. So this is x, this is 0, and this is 1, because the proportion x can be is between 0 and 1. Now when this is x is 0, this is minus 1, and when x is 1, this is 8. So this will be the line, and over here when x is 0, it is 2, and when sorry, when x is 0, it is 0, and when x is 1, it is 2. So this will be the other line. So there is a point at which the utility of both the species A and B meets. So in such cases, none of the pure breeds A and B are evolutionary stable, but a mix of the breeds A and B are evolutionary stable. And this is the point. We can evaluate that point. What is the point? Minus 1 plus 9x. If this is strictly greater than 2x, then A is evolutionary stable. So at this point, below this point, above this point, A is if this is strictly greater than this, then A is evolutionary stable. So it means that 7x is greater than 1 or x is greater than 1 by 7. So this point is actually 1 by 7. And if you are below this point, so if you are below, x is below this point, then what happens is this eventually come down to this point. So this equilibrium is a kind of mixed strategy Nash equilibrium, which we have studied in previous weeks, I guess week 2 or week 3. So this is similar to that idea, but in evolutionary game theory. What does this mean? It means that these two proportions, 1 by 7 and other will be 6 by 7. So when you introduce x in this population of 1 minus x of species A, the equilibrium will converge to x being 1 by 7 and 1 minus x being 6 by 7. That equilibrium will be reached. Therefore, the population of A will be in the proportion 6 by 7 and the population of B will be in the proportion 1 by 7. And this is the evolutionary stable strategy. All right. This is a mixed evolutionary stable strategy. Is this okay?
Okay.
So this is another question on evolutionary stable strategy.
So intruders are always in less in proportion.
Yes, yes, intruders are less in proportion, and you want to see while introducing these introducers, will the intruders population increases or will they perish? That is the question. If they remain in the population, then it becomes evolutionary stable, and that is how evolution has been carried out in our world.
Okay.
Right? So this is yet another question where you can check for evolutionary stable strategy. So this is a payoff matrix. Could you tell me which of the following strategy or which one of the following strategy is evolutionary stable?
D is evolutionary stable strategy.
Okay, so before solving this problem, I'll just go back to the previous problem, this problem. You see, we knew that LB is a dominant strategy. Therefore, we already know that this will be a evolutionary stable strategy. We can use this idea as well. You see, we had three cases, two cases. If A is greater than C, so this is the payoff matrix: A comma A, B comma C, C comma B, and D comma D for S, S dash, and S, S dash. All right. So if one is A is strictly greater than C, or when A is equals to C and B is strictly greater than B, then S is evolutionary stable strategy. So you can use these ideas as well to solve the problem instead of doing that um, that this graph form. All right. Now we can go over here. When you obtain that D is a evolutionary stable strategy, how did you obtain it?
I just drawn the graph.
Right. So you just equated the utilities and then obtained. Before that, you could use the idea of strictly dominant Nash equilibrium. If that is the case, then you don't need to do all of those, because one of the two conditions for evolutionary stable strategy is already met. What is the condition? First condition is A is strictly greater than C, or when A is equals to C, B is greater than D.
D.
Right. So over here you see, if you name this as A comma A, B comma, sorry, this is B comma C, and this is C comma B, and this is D comma D. So A is not greater than C, or A is not equals to C. So these both conditions are not met.
Right.
But if you invert this table, DC, DC, if you invert this table 1 comma 1, 0 comma 3, t comma 0, and 2 comma 2. Now when you say A is greater than C, is A greater than C?
Yes.
Now you don't need to do all of those. When A is greater than C, this condition is already met, and you can just say it is evolutionary stable. But this is not just evolutionary stable strategy. It is a strictly dominant strategy. You see, 3 is strictly greater than 2, 1 is strictly greater than 0. Therefore, D is a dominant strategy for first player, and D is the dominant strategy for the second player. Therefore, D comma D is a strictly dominant Nash equilibrium, and therefore D will be an evolutionary stable strategy. So we solved this problem using three techniques. The first idea was strictly dominant Nash equilibrium, using the idea of strictly dominant Nash equilibrium. If you solve this, then you will find that D comma D is a strictly dominant Nash equilibrium. And if any strategy set is a strictly dominant Nash equilibrium, then it will be surely an evolutionary stable strategy. So we solved this using the first idea. The second idea we used is this idea. These are the two conditions when a strategy can be called as evolutionary stable strategy, but this is the case for uh, two strategies, each player having two strategies. Remember that. Okay? So when this happens, then we can say that it is a evolutionary stable strategy. And over here, condition 1 is met. Condition 1 is met. So in this way also, using this idea, we can say that D is an evolutionary stable strategy. The third idea which we used is using the utility functions. So you calculate the utility each of the players are getting using utility functions and plotting them. Okay. So we use three ideas, and by the way, all the three ideas are using utility in one way or the other. So utility is the main key of obtaining a strategy to be either Nash equilibrium or any other thing. All right. So the idea which we used that in the lecture this was the case and it will happen here, which is not true. Utility plays an important role in whatever we are talking about. All right.
Okay, so we transposing a matrix doesn't affect because this is a symmetric game, right?
Over here we did not transpose. We just moved the strategy in the. We just swapped the two strategies. We did not transpose it. This is not a transpose of this matrix, by the way. Just change the position of how we are writing the strategies. We just moved D one step above the other strategy, and the other way in the column row. Did not transpose it.
Okay, got it.
Just a different way of writing the same table. Right? So this is the correct answer. Any questions from other participants? All right. So over here, I have moved on to, so we have talked about evolutionary stable strategy. What is the idea of evolutionary stable strategy? The idea came from how new introduction of new individuals in a population changed the dynamics of the whole population. So they had an initial population and they wanted to study whether introducing some new population changes the proportion of the original population or not. From that idea, they formulated it. They used some notations to say which population will be, which species will be benefited in that population, and that got into the form of a utility function. And then they saw a similarity between evolutionary study and game theory, and therefore they combined it and merged that field to originate the idea of evolutionary game theory. And in such cases, we do not call players, we name this as population of species. And those are not strategies, those are individuals of species interacting with other individuals of the species. So if you go back to the first problem of evolutionary game theory, this statement was long. What was the statement? It says that each beetle repeatedly pairs with other beetle for food competition in its night time. So what is doing? So two beetles are interacting with one another, and in this whole interaction, two beetles never meet each other more than once. So you see, we assume that the population of the beetles are large enough so that two beetles never have a significant probability of interacting with one another more than once. So what is happening is those beetles are interacting with one another, and never one beetle meets the other beetle twice or more than twice. Okay. So in such cases, it is a random mixing of this new introduction of new species with the other individuals of the species, and therefore such a long definition of the problem is given. Okay. And this idea is discussed in the lectures as well. Okay. So this was the whole idea of evolutionary game theory. Any questions? All right. So we'll move on to the next part of this week's, which is repeated games. Okay. So this is a game where we have C and NC as the strategies of the two players. So we are back to the normal form game, and we'll talk about players or two individuals, I1 and I2. So this is a public good game. So this problem we had discussed in our, I guess, first or second week, where you can choose to contribute or not contribute to a public good. If both of them contributes, they get a higher utility. But if one contributes and the other doesn't contribute, the one who is not contributing has a more utility than the other. So one is actually paying more and the other is just using. So for example, you are pairing up for an assignment, and one person is doing all the work and the other person is not doing any of the work. But the grade of the assignment will be given equally to both of the students. In that case, one benefits and the other is penalized. And this is like that public good game. All right. So, and if both doesn't contribute, then their utilities are very low. It can be 0 as well. I have just written as 4. And this is just symmetric. So this is the table. Now the question is, if this game is repeated 50 number of times, what will be the Nash equilibrium strategy profile? Did you understand the question? If you're speaking, you are not audible, right?
Yes, this means the outcome of the one game is known, and then the second game is played.
Right.
And
And players
similarly,
can,
the outcome of the 49th game is known, up till 49 games are known, and then the 50 game is played. So the question is whether the Nash equilibrium will remain same or it will be different or adjusted accordingly. So that is the question.
No, that question is not that. It says that if you find the Nash equilibrium of this game when it is repeated 50 number of times, so overall Nash equilibrium of the entire game repeated 50 number of times, what will be the strategies of the players, strategy profiles? So you remember when we were talking about extensive form game, we write the strategies as combination of actions. So this 50 repetition is kind of a extensive form game. One game is played, a simultaneous game is played, and then the results are used for the second game, and so on and so on and so forth. So this is an extensive form game which is repeated 50 number of times. So in the lecture, if you go back, there was a game of entrant, and that entrance game. So where there was an individual who wanted to enter the market, and the already existing player could either fight or accommodate. So that was one game, but it was played multiple number of times. So this is the same game. This game is played 50 number of times sequentially. The question is, what is the strategy profile that will occur in Nash equilibrium? So strategy sets are written in tuples, this long tuples, all right. You remember, right? In extensive form game, strategy sets are written in this form.
Sorry, can you come again? What did you ask?
I'm asking, in extensive form game, the strategies are written in this form. You recall that, right?
Oh,
If you don't remember,
sorry,
I'll just
remember.
Okay, I'll just help you. So suppose this is a entrant and deter. I don't remember the other player's name. It was entrant and something else. So a player wants to enter the market. So I'll just say player one and player two for my convenience.
Incumbent.
So a player, incumbent, right? So a player wants to enter the market. If he enters, then the incumbent can either fight or accommodate. Right? So if he enters, the incumbent can either fight or accommodate, and the entrant can either remain out or enter. All right. So you can just write the utility. That is not important over here. As far as I remember, it is -1, and this will be 2, 2, and this will be 0, 3. Okay. It is not the material. Now, when I say what is the strategy of entrant, so can you tell me one of the strategy, any one strategy of the entrant? It is either E or O. Okay. These are the two strategies of the entrant. Now, suppose this game is played repeatedly. When I say this game is played repeatedly, what will happen is at each of these node, you will have another node. This will be entrant. He can either enter or remain out, and the incumbent has two options, either to fight or accommodate. Now, in this game, suppose this is the game. Right? Suppose this is the game. Can you tell me the strategy of entrant? Is it E? Just E. It will be combination of actions E, 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 O. Remember, this is how we discussed.
Yes.
So the strategies in an extensive form game are written in combinations. So that is how it is written here. So 50 simultaneous games are being played, and what will be the combination of those strategies? Not combination of the strategies, it is known as strategy profile. It is combination of actions. So again, the question over here is, if this game, public good game, is played 50 number of times, what is the equilibrium strategy profile? Nash equilibrium strategy profile. If you don't understand, could you help me find the Nash equilibrium of this one stage game?
4,
So suppose this is the
4, 4.
No, 4, 4 is not the Nash equilibrium. NC, NC is the Nash equilibrium. Okay. NC, NC is the Nash equilibrium. 4, 4 are the utilities each of the players are getting.
Okay.
Now, this is for one stage. Now, when we solve sequential game, we use backward induction to solve the problem. All right, so suppose we are using backward induction to solve the problem. In the last game, NC comma NC will be the Nash equilibrium. All right, now this will be known at the 49th stage, and 4 comma 4, a constant number 4 comma 4 will be added to all the utilities. So it will become 14 comma 14. This will be 6 comma 16. This will be 16 comma 6, and this will be 8 comma 8, right? So adding a constant number to all the utilities doesn't change the utility at all. Is that right?
Right.
Therefore, what will be the Nash equilibrium in the 49th game?
It will still remain the same.
Right, it will still remain the same, NC comma NC, and this will remain for all of the stages, all 50 stages. NC comma NC will be the Nash equilibrium. Therefore, the strategy profile for one of the player will be NC comma NC comma dot dot 50 number of times NC for the first player, and for the second player NC comma NC dot 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 NC till the last. So 50 number of times for the first player, 50 number of times for the second player. And since this is a symmetric game, you can just write one of the strategy profiles. Therefore, this is the strategy profile adopted by a player at Nash equilibrium for this game, which is repeated 50 number of times. I will repeat again. Therefore, this is the strategy profile at Nash equilibrium for this game when this game is repeated 50 number of times. Is it all right?
So this conclusion we have deduced from backward induction.
Right. Has been reduced from backward induction. And this was done in Sir's lecture as well. If you have seen Sir's lecture, a similar problem was solved using backward induction in Sir's lecture.
Couldn't we have said that NC is a dominant strategy when the first time it is played, second time also it is played and all that, and hence can we use that logic and say it is always be NC?
Yes, this is not just a Nash equilibrium. This is a strictly dominant. No, it is. Yes,
yeah,
it is
a dominant. Yeah, so it automatically is a. So that's why that will be the
same logic will be applied, and this will be the solution to the problem. You see, this is higher than this, and this is higher than this. Therefore, NC is a strictly dominant strategy for both the players. Symmetric game. So for one of the players means for the other player as well. All right. So is this okay?
Yeah.
All right. So we'll move on to the next problem. So this is also about repeated games. Now it says, so this is a theoretical question and it was discussed in the lecture. So just take a minute to read and tell me the answer. If you face any issue, you can ask me. So do you remember this game? Which game is it about? Which game is it about? Okay. So this game is about, this is about the game infinitely repeated prisoner's dilemma. All right. So it is about infinitely repeated prisoner's dilemma. And if you recall, in week 4, I had discussed this grim trigger strategy. And I have taken a problem again in this session. Subsequently, we'll see that problem. What is this grim trigger strategy and tit-for-tat strategy? Anyone want to participate? What is this tit-for-tat and grim trigger? You can just tit-for-tat is well-known strategy.
If prisoner one chooses deny, then prisoner 2 will also choose deny. This is tit for tat.
Not exactly correct. You are in the correct direction, but the explanation you gave was not correct.
Okay.
You see, I'll just write a prisoner's dilemma game table. Okay, so this is confess, deny, and let me write some. So it is 2, 2, 3, 0, 0, 3, and 1, 1. I hope I am written. Yeah. Yes. So you see, over here, D is strictly dominant strategy. So 3 is more than 2, 1 is more than 0, and the other for the other player as well. Now, this game is repeated infinite number of times. When a game is repeated infinite number of times, the player can decide to play. So you see this 1, 1 is actually worse payoff than 2, 2, which they can get if they cooperate. So in the long term, they can decide to cooperate with one another, 2, 2, and they can say, if you deviate from this, if you play any other strategy, I will copy you in the subsequent uh, game. So suppose in the first game, both played C, C. In the second game, suppose player 1, so this is player 1 and player 2. Suppose in the second game, player 1 defected. So you see when player 1 defected and player 2 is playing C, player 1 is getting 3 and player 2 is getting 0. So this is actually player 2 is penalized. So what player 2 will do, he will say, I will penalize you back. So in the third game, he will repeat what player 1 has played. He will play D and player 2. So if one player, so player 2 is playing tit for tat, he will just do whatever the other player has done in the previous round. All right. And if both the players are playing tit for tat, so they will repeat each other's strategy. So player 2 will repeat D and player 1 will repeat C. In the fourth stage, they will just exchange. So player 1 will play D and player 2 will play C, and so on. So this is a tit for tat strategy. Both players are playing tit for tat. Whatever you do in the previous round, I will do in the next round. This is tit for tat. What is grim trigger strategy? Grim trigger strategy says that if you defect once, suppose we are cooperating, and if you defect once, I will defect forever. So suppose player 1 defects in the second round and player 2 did not know that. So player 2 played C. Player 2 will say, you have defected, so you have not maintained the discussion we had. Therefore, I will always play D no matter what. I will always play D. No matter what you play, it doesn't matter, I will play D. So this is kind of penalizing both. So this payoff of first player is also reduced, payoff of second player is also reduced. So this is grim trigger strategy. Okay. Is this all right?
Yes.
Now, the question is credibility and deterrence. What is credibility and deterrence? You see, I will explain because you are not able to, I guess you are not able to understand the problem. If that is so, I'll just explain. You see, what is credibility? I had discussed credibility in one of the previous problem solving sessions. it says that whatever threat you are giving should be credible. It should accompany your utilities. So your utility should reflect that threat. If that threat, so if that threat is not credible, then your utility will not align with what you are saying. What I mean by that is, for this grim trigger strategy, suppose player 2 says, if you defect, I will defect forever. What does this mean? He is not only penalizing player 1, he is also penalizing himself. So this threat is not credible. Player 1 will think, why will he get a utility of 1 when he can get a utility of either 2 or 3? So playing D forever might not be, so he's just giving me a false threat, something like that. So grim trigger strategy is not, it lacks credibility. You can play grim trigger strategy, that is not a problem. But if you threat someone that I will play grim trigger strategy, that might not be credible. Okay, so actually this is true. Grim trigger strategy lacks credibility, but has deterrence. Okay, so we had talked about credibility for grim trigger. All right. What is deterrence? Deterrence means you will refrain someone from doing otherwise. What I mean by that is, when player 2 says that if you defect, I will defect forever, it means that if that occurs, the utility will be reduced forever. So this threat, if that is true, if player 2 does that, then player 1 will be worse. So this is kind of not making player 2 do that. So that is deterrence. It is not allowing player 2 to defect. So it has adequate deterrence. It actually has a lot of deterrence. All right. It is not credible, but it has deterrence. Is this all right? If you communicate, I'll understand that I'm making you, I can make you understand. All right. So I assume you have understood. Now for tit for tat, you see, we will talk about credibility and deterrence. Whenever tit for tat is being played, suppose tit for tat is being played by player 2. Player 2 says, whenever you defect or whenever you do whatever we have discussed, whenever you do other thing, what we have discussed, I will punish you. So this is kind of punishing him. You see, what is the utility for this case? Player 1 is getting a utility of 3, player 2 is getting a utility of, sorry, player 1 is getting a utility of 0, player 2 is getting a utility of 3. So therefore player 2 is punishing player 1 because he has defected in the previous round. He has not played the same strategy. So this is kind of a punishment. So you see, this punishment is immediate. Immediately he is punished. Therefore, and in the other round, you see, this is getting 3 and this is getting 0. And this will alternate. In the next round, this will get 3 and this will get 0. So this is a credible threat. Player 1 knows that player 2 can do this because his utility is not reduced forever. So player 1 knows that player 2 can do this. Therefore, this is a credible threat. But this is not so it lacks deterrence. Why? Because you see, changing from defect to um, defect to sorry, what is this? See, sorry, could you help me? What was C?
C was cooperate. No?
Yeah, yes, sorry. So what I was saying is, so deterrence. So you see, player 1 knows if he defects and then cooperates and then defects and then cooperates, it doesn't matter because the utility is not always reduced forever. So it lacks deterrence. It has credibility, but it lacks deterrence. On the other way, grim trigger lacks credibility, but it has adequate deterrence. So 1 and 2 is true. Therefore, this is the correct answer. Is this all right? You can ask me. This is important concept to understand.
Why are you not checking out 3 and 4?
So it is just okay. So grim trigger strategy benefits the punisher too much. So it doesn't benefits anyone. Grim trigger strategy, then it always punishes both of them. So this is wrong. tit-for-tat strategy punishes the misbehaving player too much. Actually, tit-for-tat strategy is kind of even for both the players. So if both the players are playing tit for tat, in one round one will benefit, in the other round other will benefit. So it is not asymmetric, it is symmetric. All right. So this is also not true. This is all right.
Yeah, okay.
Okay. So I have one more game over here. So before this, you can just take 5 minutes break and then we'll meet in 11:16. Okay. In the time being, if you want, you can solve this problem. I'll not move this. Let's mute myself. Just a minute. Yes. So, did you get time to go through the problem? Am I mute or am I audible? Yes, I am audible, right? Yes, I am audible. Hello.
We can hear you.
Right. So, what are the thoughts? What are your thoughts on this problem? Okay. So you see,
I think
in
bad
this,
and by the bad and by is what will happen.
so you see when you say bad and buy, this is for one stage. This game is played 50 times, alright? So you should specify whether this bad and buy is for one stage or all the stage.
I think it is for all stages, but that option is not there. So maybe I'm wrong.
Alright. So we will see what happens. So you see, for player one, so we'll, because this is about game theory, we'll talk about player one and player two. So we have two players, player one and player two. Player one can either, so this is in the context of goods and consumer and goods, consumer and manufacturer. So a manufacturer can either produce a good product or a bad product. A consumer can either buy the product and not buy the product. All right. So that is the context of this game. So when player two buys the product, player one's strategy, I'll just use a highlighter. Player one's strategy is to make a bad product. When player two is not buying the product, player one's strategy is again to make a bad product. On the other hand, if player one is making a good product, the utility of buying is more than not buying. On the other hand, if player one is making a bad product, utility of not buying is more than buying. Is this all right? Therefore, we have a Nash equilibrium. This is the Nash equilibrium. Okay, so this is the Nash equilibrium of a one-stage game. Now the question is, what will be the subgame perfect equilibrium actually for this case? Using backward induction, it means that if you are playing this game 50 number of times, what will be the subgame perfect Nash equilibrium for this game? So you see, in the last stage, the last stage, we know the Nash equilibrium. What is the Nash equilibrium? Player one will make a bad product and player two will not buy. This will be the utility, and that strategy in the last stage will be bad and not buy. Now, when we come back in the second last stage, the same game will be played. And in that case also, bad and not buy will be a Nash equilibrium. And when you come sequentially to the first stage, you will again get bad and not buy as the Nash equilibrium in that stage. So for the whole game, when it is repeated 50 number of times, player one will always play bad, 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 and player two will always play not buy, not buy, not buy, not buy. Therefore, bad, comma, not buy will appear in each period. So this is the correct answer. Any questions?
I don't have questions.
Any other participant? Any questions?
I just have a question. Maybe it is a silly question, but when in a repeated game, the Nash equilibrium doesn't change. Okay, then what is the purpose of studying these repeated games?
So for this simple game, you have just one Nash equilibrium, but there can be multiple Nash equilibriums in a game. Alright. So in those cases, you will not get one strategy for the whole game, which is a Nash equilibrium. There will be multiple strategies and there could be multiple branches of strategies which lead to a Nash equilibrium. In such cases, the game becomes complex. We are not going into those complex games.
Okay. And also we have studied till now, there is an interaction of two players only, so that we can draw them on the table. What happens in the cases when there are multiple players?
So you see, we are actually, when we study in real life problems, there can be more than one players. What we do is try to reduce the number of players in the game by grouping the players. Suppose you're talking about a community and government. In those cases, you cannot say every individual is a player or the government. So government is just one, but every individual is a player. You cannot say. So you can group the individuals in one group, saying community and government. So in that case, you have two players. Suppose you cannot group the players in two games, then you can have multiple players, 3 players, 4 players, n number of players. And I have also solved such problems in my previous, I guess, first week or second week's lecture. You can go back and check. In those cases, we just cannot draw the game table. We have to use the idea of calculus and differentiate the utility of each of the players to get the best response of each of the players. And then we get the intersection of the best response of each of the players, which gives the Nash equilibrium. So go back and see the lectures. If you don't understand, we can discuss in the next lecture.
Okay.
All right. Okay, so we'll move forward. So this problem, we had discussed the same problem in week 4, but I have changed the utility values. Okay, these values are changed. This is the same problem which we had discussed in week 4. Go through the problem and then we can discuss about this problem. Any thoughts? Shall we discuss?
Yes, please.
So, do you remember how? Okay, so you see, we have two players in this infinitely repeated prisoner's dilemma game, and we are talking about dream trigger strategy. What is the strategy? We will cooperate until the first defection arises. If someone else defects, I will defect forever. So this is the strategy. Or you can think about it like this: if you are playing a grim trigger strategy, whether you want to defect first or not, that is the question. Will you defect first or not? if you defect first, then you are not playing grim trigger strategy. The other player may play the grim trigger strategy. So the question is, playing grim trigger strategy, when will that be a subgame perfect Nash equilibrium? Okay, so this is the question. So if you are playing grim trigger strategy, that will only be a subgame perfect Nash equilibrium when any other strategy apart from the grim trigger strategy has a more utility than grim trigger strategy. That is the idea. This is same as the idea of other Nash equilibriums as well. What is a Nash equilibrium? You have no incentive to deviate from the given strategy. That is the best response. And in Nash equilibrium also, you have no incentive to deviate. So over here, we will see that playing grim trigger strategy, and we will see playing another strategy from grim trigger strategy. Whereas the utility of playing grim trigger strategy is more than the utility of playing any other strategy, then we will say that grim trigger strategy is a subgame perfect. For that value of delta, grim trigger strategy is a subgame perfect Nash equilibrium. Okay, so you see, we will just draw the game table quickly. Is cooperate and defect, cooperate and defect. So this is 3, 3. This is 1, 4, 4, 1, and 2, 2. So this is the table, game table. So what is the utility if someone plays grim trigger strategy? Can you tell me what is the utility if someone plays grim trigger strategy? So before that, suppose both the players are cooperating for X number of periods, and X plus 1 period, the other player is defecting. So what will happen? We will have CC. So this is for player 1 and this is for player 2. CC, 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 dot, 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 CC. When the other player defects, I was cooperating, so I will cooperate, but I will defect forever. No matter what the other player do, I will defect forever. So this is grim trigger strategy. Now, when you play this grim trigger strategy, you know that cooperation is better than defecting. So the utility you will get with grim trigger strategy will be cooperate, 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 cooperate. That will be the utility you will get, which is 3 plus 3 plus 3 plus 3 plus 3 dot dot dot. Now you just cannot add 3 for subsequent periods because of the idea of discount factor. You can go back to the sir's lecture and see what is a discount factor. If you don't understand, tell me. I'll just briefly describe what a discount factor is. So this will not be 3 plus 3 plus 3 plus 3. The future value of utility will be discounted. So in the first period you will get 3, in the next period you will get 3 delta, and so on. 3 delta square, 3 delta cube, dot dot dot. Okay. Now, if you don't play grim trigger strategy, you start defecting. So suppose you are the one, so you are not playing grim trigger strategy. You are playing some other strategy. What is the strategy? You defected in the first round. So if you want to defect in the subsequent round, why not defect in the first round? That is the idea. So what is the utility you will get? In the first round, when you defect, you will get a utility of 4. In subsequent round, you will get a utility of 1, which will be 1 times delta plus 1 times delta square plus 1 times delta cube, and so on. Okay. So this is the another strategy from grim trigger strategy. So when will grim trigger strategy a subgame perfect Nash equilibrium? When the utility you are getting by playing grim trigger strategy is strictly greater than the utility you are getting when you are playing any other strategy. Is this all right? All right, so I assume it is all right. Now this is an infinite sum, and this sum is actually given by 3 times 1 by 1 minus delta, but delta is actually the GP factor. Okay. So how is this actually done? I'll just write one more step for you to understand. So this is actually delta. So this is, you take 3 common, it will become 1 plus delta square plus delta cube dot 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 dot. So you just multiply 3 times, and this sum is actually 1 by 1 minus delta. This is the sum. Over here, what you do, you take 4 plus and 1 common, so it will become delta plus, okay, not 1 common, delta common. Take delta common. 4 plus delta common, so it will be 1 plus delta plus delta square plus delta cube plus dot on dot. Okay. So this will be greater than 4 plus delta times 1 by 1 minus delta. Is this all right?
Yeah.
Now you can just compare the two utilities and you can just obtain what will be the value of delta. So I guess I'll just do it. So this will be 3 by 1 minus delta is greater than 4 plus delta by 1 minus delta. And if you solve this, whatever the value of delta is, doesn't matter. When you solve this, that will be the value of delta for which Grimm-Trigger strategy is the subgame perfect Nash. Could you help me find the value of delta quickly?
One by 3.
Delta is greater than 1 by 3. Please check again. I guess it is half I, as far as I remember, and just solve it once. It is 3 greater than 4 times 1 minus delta plus delta, which is actually 3 greater than 4 minus 3 delta. Yeah, 1 by 3. All right. Now we'll move on to another game where we are talking about tit-for-tat strategy. In the previous game, we have seen this for Grimm-Trigger strategy. Now we'll see about tit-for-tat strategy. Is this all right? As far as I remember, it is not 1/3, it is half. Where did I do wrong? Okay, so this is where I did wrong. You see, when players defect, they get a utility of 2 and not 1. Alright, so they get a utility of 2. So this will be 2. And this will be 2 times delta. 2 will come over here, 2 will come over here. And if you solve this, this will be 2. And this will be what? 4 minus 2, this is 2. And 2 delta is greater than 1 and delta is greater than half. Okay, so it was half, not 1/3. I'm sorry for that. So what is happening is when they are defecting, they are getting a utility of 2 and not 1. Is
Yeah,
that all
okay.
right?
Okay, okay.
So it was an error from my end. All right, so this is the same game. Now we are playing tit-for-tat strategy. So one thing I would tell you at the end is that obtaining a subgame perfect Nash equilibrium for tit-for-tat strategy is actually very, very difficult, or we can say it is not possible. But I have restricted that game. What is that game? I am saying that on the path of play, what it means is everyone starts with cooperation. So the game starts with cooperation. That is the restriction I am making. So the first stage starts with cooperation. That restriction I am making. Okay. Now just have a minute and read the problem, and you can help me to solve the problem. That would be more better, I guess. Any idea how to proceed? So the question is whether you play tit for tat or not. So what we have to show? We have to show that the utility of playing tit for tat is more than the utility of playing any other strategy. If that is the case, then we will play tit for tat, or tit for tat is the subgame perfect Nash equilibrium. So what is tit for tat strategy? Whatever player 1 does, so suppose we are player 2, whatever player 1 does, I will do the same, and player 1 will also do the same, because we're talking about subgame perfect Nash equilibrium. So it is a symmetric game. So whatever player, so if player 1 is playing tit for tat, player 2 is also playing tit for tat. Our aim is to show that if I play tit for tat, our utility will be more than what I will get when playing any other strategy. If that happens, what is the value of delta? If tit for tat is a subgame perfect Nash equilibrium, find the value of delta. So you see, do you want to speak up? You see, when we play tit for tat, and the game starts with CC, it will always be CC, because you see in the previous stage, player 1 played C, I will play C. Player 2 played C, I will play C. So it will always be CC. This will continue. What can be another strategy? So suppose we started with CC. The other strategy will be in the next game, I will play D and not CC. Okay, I will not play what you played in the previous round. Alright, it doesn't matter what the other player is playing. I will only talk about player 2 because I'm trying to find out the utility of player 2 now. Okay, and then I will play CCC. Or we can say no, it will be I will defect but remain in the tit for tat zone. So what it means is I will not play D, I will not play C, and you are playing C because you are playing tit for tat, but I will, so this will be D, and I will again come back to C, and then you will play C, I will again come back to D. This is all right. So I was the one because of me. So we are player 2. What are we? We are playing 2. Because of me, the tit for tat strategy was, so I was the one who deviated from the tit for tat strategy. Previously, we were playing tit for tat strategy, but I was the one who deviated from the tit for tat strategy. So my aim is to find out the utility when I am playing tit for tat strategy versus the utility I'm getting when I'm not playing the tit for tat strategy. Is this all right? So previously, I was playing tit for tat strategy. Yeah, go on.
It is saying when on the path of play, that means the game has started, where the game starts with everyone cooperating. Once the tit for tat starts, one guy starts defecting, I don't think it will ever come to a stage where everyone starts cooperating, no?
I did not get your question.
No, I was just trying to understand the English written here in the question. It says find the subgame perfect Nash equilibrium when on the path of play, the last words, where the game starts with everyone cooperating.
Yes,
That
so you
means
see,
if the tit,
sorry, continue.
so if someone has done tit for tat, then after that they will never start cooperating. So is it asking like when in the future they will start cooperating? They will never
No,
cooperate in future.
no. Tit for tat means whatever you played in the last round, whatever the other played in the last round, I will play the same.
I understood. But the question says when they will start cooperating, where the game start. Acha, it is
So
not for the
where is
future.
a
It is saying.
condition? It is a condition.
Acha,
It
it
is a
is saying
condition.
assume by everyone is starting to cooperate. Okay, okay,
Okay,
fine. Okay.
it is a condition. So again, so we are starting with cooperate. Okay, so I'll just highlight this. We are starting with cooperate in both the games.
Okay,
In
so
one
when you
game,
will calculate CC ka delta ka whatever that utility, and then CD the way you did in the previous one, and then calculate which delta is higher. The same
yes,
method, right?
yes. So help me. What is the utility in the first for this strategy for player 2?
It will be C plus C delta plus C delta square, same as the earlier one. So it will be
Yes,
3 into 1 upon
1 upon 1 minus
1
delta.
minus delta.
For this, what
Correct.
will be the utility?
For this, it will be 3 plus D delta plus
So
C
what is
plus
D?
D delta plus C delta square.
So
What is
D
D?
is
What is
1.
D? 2. No,
No. One is playing D, the other is playing C. So whoever plays D will get a utility of 4.
4. Yes. Okay. So 4 delta
4 delta
and then 1 delta square.
plus 1 delta square plus
Then 4 delta cube
4 delta
delta
cube,
cube plus 1 delta raised to 4
4 and so on.
and so on.
Right? So this is what we are getting. Now we are starting here with time 1. We can always remove time 1 because if it is time 1 or time n, it doesn't matter. After time 1, what is the thing is happening we are interested in, right?
Yeah, so 3 3 getting cancelled on both sides. That's what we are.
Yes. So we will no, it will not happen like that. You see, we are starting over here. We are starting over here, right? So just 3 and 3 will not cancel out. We are interested from time point 2. Over here, we will say from time point 2, I got 3, and from time point 3, I got 3 delta. From time point 4, I got 3 delta square, and so on. So this will remain as 3 by 1 minus delta. But this game, this 3 will not be there. We will start with delta, but this delta will not be there. So it will become 4 plus delta plus 4 delta square plus delta cube plus dot dot. Is this all right? We are starting at time point 2 and not 1 because 1 is not a specific time. It can be n times because we had cooperated for n number of times. But when we are defecting from that time on, we are interested to find the utilities. So we will start at time point 2 and not time point 1. Is that all right?
Okay, fine.
Just think about it. At time point 0, we were getting 3. So if you just remove 3 from both the sides and we can just take delta common. So what did we do? I'll just erase this green part and
Yeah,
I'll
okay,
make
understood.
you
It'll anyway turn out to be the same thing that you have written.
the same thing. Yes. Sorry. It will turn out to be the same thing. Okay, so what is this sum you see? We can take 4 common. So we have 4 times 1 plus delta square plus delta 4 plus delta 6 plus 1 times, not 1 times, delta times 1 plus delta square, 1 plus delta square plus delta 4 plus delta 6 dot dot dot. This is also dot dot dot. Is this all right? Just
Yes,
check.
clear.
So you can just find what is the sum. So this will become 4 into 1 by 1 minus delta square. And this will become delta times 1 by 1 minus delta square. Because delta square is the ratio. It is not clear. I'll just write it over here. This is what 4 times 1 by 1 minus delta square plus delta times 1 by 1 minus delta square. Is it all right? This is the utility I'm getting from not playing tit for tat. This is the utility I'm getting by playing tit for tat. So we'll just equate it. 3 by 1 minus delta is greater than 4 times 1 by 1 minus delta plus delta times 1 by 1 minus
Delta
is it all
square.
right? Yes, delta square. Okay. Now we'll just solve this. So this will be 3 into 1 plus delta greater than 4 plus delta. Is it all right? Because I have written 1 minus delta square as 1 minus delta times 1 plus delta. Okay. And I have cancelled out 1 minus delta from the denominator. So this will become 3 plus 3 delta is greater than 4 plus delta, which is what? 2 delta is greater than 1, or delta is greater than half, or maybe equal to also, because weakly dominant strategy can have equal to. Delta greater than equals to half. When this happens, then tit for tat becomes a subgame perfect Nash equilibrium, provided the game starts with cooperate. Is all right?
Yes.
So this is the solution for this problem. Now, I was telling you that tit for tat doesn't have a subgame perfect Nash equilibrium. We'll see that when we consider that we did not start with cooperate. We started with either DC or CD. So that is the next problem. So this is the same problem where, so this is known as off the path, where one is cooperating and the other is defecting. So CD, or it can be other way around also, DC, doesn't matter, because player one in this game is symmetric, so it doesn't matter. So this is how the game starts. One is defecting and the other one is cooperating. So suppose this is the case, player one and player two. So when we play tit for tat, what should be the, so this is point one, what should be at time point two? This will be defect and this will cooperate. For time point three, this will cooperate and this will defect, and so on. This is tit for tat strategy. What will be a strategy which is not tit for tat? So the first stage was DC, but what will I do is I will not play D, I will play C. So I am player 2. We are talking about player 2 here. We are player 2. So I will not play D, I will play C. Okay, and you will play C because you are following tit for tat, and again I will follow tit for tat. So C, C, then C, 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 and so on. Okay, is this all right?
What is the meaning of on the path of play and off the path of play? What did you mean by that? In the previous problem, it was on the path of play.
So actually this comes from equilibrium concepts. On the path of play means the game started with CC, and that is how the game will proceed, because actually playing CC is more beneficial. If delta value is high enough, then playing CC is better than you see, if you go back and you see grim trigger strategy, so the same values were given and delta was coming out to be, it is greater than equals to, no, it is not just greater than. So delta was coming out to be greater than equals to half. So if we have delta greater than equals to half, sufficiently high delta, then playing cooperate is always better. It will give a higher utility for both the players. So that is how this on the path of play comes, and off the path of play comes where both the players are not starting with CC, they are either starting with DC or CD. All right.
Okay.
So over here also, so we are talking about player 2, and we are not interested in the first time point, because that can be either one time point, n time point, any time point, it doesn't matter. At the time point when we started playing some other strategy, from that time point we are interested. So what is the utility over here for the player 2? Player 2 in the first in time point 2 he will get 4. In the next time point he will get delta square, and in subsequent time point he will get 4 delta, not delta square, it is delta. In subsequent time point he will get 4 delta square, then delta cube, then again so on. And over here this will be same as, so 3 plus 3 delta plus 3 delta square plus 3 delta cube, and so on. Now if you look carefully, this utility is same as this utility, and this utility is same as this utility. Therefore this will become 3 by 1 minus delta, and this will become 4 by 1 minus delta square plus delta by 1 minus delta square. Okay, and what are we saying? If this value is more than equals to this, then tit for tat will become a subgame perfect Nash equilibrium for the value of delta we are obtaining. So what are we saying? We are saying 4 by 1 minus delta square plus delta by 1 minus delta square is greater than equals to 3 by 1 minus delta. If you evaluate again, delta will be less than equals to, in this case, will be, so if you evaluate, you can just check once, it will be less than equals to 1/2. Okay, so in the first case, we are saying when delta is greater than equals to half, then tit for tat is a subgame perfect Nash equilibrium. And in the second case, when delta is less than equals to half, then tit for tat is a subgame perfect Nash equilibrium. Therefore, the only value of delta which is possible for tit for tat being a subgame perfect Nash equilibrium is delta is equals to half. So delta is equals to half is the only subgame perfect Nash equilibrium when a player is playing tit for tat. Sorry, not, I'm sorry, I did not say it correctly. I mean to say when delta is equals to half, then tit for tat is the only subgame perfect Nash equilibrium in prisoner's dilemma game. Is it okay?
Okay.
Now, the interesting things come over here. This is a very specific value of delta, half. Even if delta value changes by very minuscule amount, then tit for tat will not be a subgame perfect Nash equilibrium. Therefore, obtaining a subgame perfect Nash equilibrium, so tit for tat is generally not a subgame perfect Nash equilibrium for a prisoner's dilemma game with infinite repetition. That is the conclusion of these two problems combined. Because particular value of delta, obtaining a particular value of delta is very important. You see, delta is actually in a continuous range between 0 and 1. So a continuous variable obtaining a particular value, that probability is actually 0. You go back to the probability lectures and you will remember that a continuous random variable taking a particular value, that probability is 0. Therefore, we generally do not have a subgame perfect Nash equilibrium for tit for tat strategy in a repeated prisoner's dilemma game. All right.
Okay.
So that is it for this class. Thank you so much. We will meet
thank
in
you.
the next class. I hope today was helpful.
So I
Thank
have
you
not
for joining.
seen this week's lecture, so that's why in that initial part I wasn't, but then once this other stuff started coming, I could follow. Thanks.
No problem.
Thank
Sure.
you.
Thank you.